Hello. In this class we will discuss damped harmonic oscillator. That means a harmonic oscillator which experiences damping force. Damping force means frictional force. Now here we consider a special type of frictional force, viscous force, which is the frictional force experienced by a body when it moves through a fluid. It can be a liquid or it can be a gas. So we are considering a harmonic oscillator um, oscillating in a fluid. Okay, it can be in normal situation. You think about a simple pendulum, okay, which is oscillating in air. So this air is a fluid which exerts a viscous force on this bow. Okay, so this is our model, a harmonic oscillator which is moving through a gas or a liquid, in general a fluid, so it experiences a viscous force. So we are talking about a mechanical oscillator, but this model is applicable to a wide variety of situations. For example, um, consider the oscillation of electric current in certain electric circuits. Now there, the resistance of the electric circuit acts as the damping force. Okay, there it works in the same way as the viscous force on a simple pendulum. Okay, oscillating in air. So what is this viscous force, or what is this damping force? The damping force we can write as, so the damping force we can write as minus some constant b into v. Here v is the instantaneous velocity of the oscillator and b is some constant. This constant depends upon the shape of the oscillator as well as the medium, the viscous medium through which it is oscillating. So you can see that this damping force is directly proportional to the velocity of the oscillator, and its direction is opposite to the direction of velocity. That negative sign shows that the direction of the damping force is opposite to the direction of velocity. So let us try to solve the equation of motion of a damped harmonic oscillator. Now we can write the total force acting on the oscillator is the spring force plus damping force. Okay, now what is the spring force? If the spring constant is k minus kx, right, and the damping force is minus bv. This is the total force acting on the oscillator. Now let us write the equation of motion. Okay, the total force is equal to, according to Newton's second law, it is mass into acceleration. So we can write these terms in terms of x. So m d square x by dt square minus kx, and let me write velocity also in terms of x. So it is dx by dt. Let us use a shorthand notation. So this first derivative is x dot and second derivative is x double dot. So x double dot represents second derivative minus kx minus b. First derivative with respect to time is x dot. So let me take all the terms to one side. So we have m x double dot plus bx dot plus kx equal to 0. Now if we divide throughout with mass, we have okay. So let me write this. So let us introduce gamma is equal to b by m. Okay, and already we know that this k by m is nothing but omega 0 square, which is the angular frequency of the undamped oscillator. Okay, omega 0 is square root of k by m, omega 0 square is k by m. So if we substitute these terms, x double dot plus gamma into x dot plus omega 0 square x equal to 0. So this is the, let's call it equation 1. This is the equation of motion of a damped harmonic oscillator. You remember the equation of motion of an undamped harmonic oscillator. There, this gamma term was 0. Okay, so we have x double dot plus omega 0 square x equal to 0. So this is a differential equation, second order differential equation of a damped harmonic oscillator. Now this these two constants, gamma, which is which can be called damping constant, and angular frequency omega 0, both has dimension um, time raised to minus 1. Okay, that means the unit we can use second raised to minus 1. Okay, you can check that the dimension of both gamma and omega 0 should be time raised to minus 1, so the unit should be second raised to minus 1. That you can get from equation 1 also. Look at the dimension of each term. Okay, and from that you can reduce, since it's a summation of 3 terms, the dimension of each term should be identical. From that you can reduce the dimension of both gamma and omega 0 and also their units. Okay, now let us try to solve this differential equation. For this we use the technique of complex numbers. Okay, so let us use that. So first I will rewrite this equation in the complex form. Okay, now for that let us introduce, we will rewrite this equation in terms of complex number. A complex number set you can write as x plus iy, where both x and y are real numbers. Okay, x is called a real part and this iy is called the imaginary part. Okay, or y is called imaginary part. Both x and y are real. When you multiply, this I is nothing but square root of minus 1. Okay, so when you multiply this y part by square root of minus 1, that is I, then that term becomes imaginary term. So this is a complex number, so we will rewrite this equation first in complex form in terms of z. Okay, and then we solve in terms of z, and finally we will equate either real part or imaginary part to get the solution. So let us see how it goes. So first I will repeat this equation in terms of the variable y. Remember, y is also a real variable. So if you rewrite this equation in terms of y, you have y double dot plus gamma y dot plus omega 0 square y equal to 0. Okay, this is equivalent to equation 1. That means our aim is to solve this equation 1, or this equation. I mean, our aim is to solve equation 1 either in terms of x or in terms of y. Okay, that means finally if you solve this equation, you should get position x as a function of time, an equation for the instantaneous position of the oscillator. Okay, for example, in the case of undamped oscillator, the instantaneous what was the instantaneous for undamped oscillator, that is ideal oscillator. When you solve the equation, differential equation, what you get is x of t is equal to some constant a. We wrote in terms of cos, right? Cos omega 0 t plus phi, where a is called amplitude, phi is initial phase or phase constant, omega 0 is the angular frequency. So this was that we obtained for undamped oscillator, position at the time t. Okay, this we obtained by solving the differential equation x double dot plus omega 0 square x equal to 0. Here our differential equation is this equation 1. We have an extra term, a damping term, gamma times x dot. So it's a more complicated differential equation. So ultimately we want to solve this equation and get x as a function of t. Okay, and we will compare with the equation of undamped oscillator. What is the change in instantaneous position? Is there any change? That's what we want to find out. Okay, so my point is, if you solve equation 1 either in terms of x or in terms of y, okay, either you will get x as a function of t or you will get y as a function of t. Whether you speak in terms of x or y, the result is the same. Okay, when you talk in terms of x, it means that the oscillator is oscillating along the x direction, and instantaneous x as a function of t means instantaneous position along the x axis as a function of t. When you write the equation, equation 1 in terms of y, which we have written here, y double dot plus gamma y dot plus omega 0 square y equals 0. Then solving this equation, what you get? Y as a function of t. So it only means that the oscillator is oscillating along the y axis, and the instantaneous position along the y direction as a function of t is the solution. So finally we want the answer either in terms of x or in terms of y. That's okay. Okay, so now we are going to rewrite this equation, recast this equation in terms of complex numbers. So what we have to do is you multiply second equation, let us call it equation 2. Let us multiply equation 2 with the square root of minus 1, that is I, all the terms, and then add with equation 1. Okay, so what you get, if you multiply equation 2 all the terms with I and add with equation 1, what is the first term? X double dot plus I times y double dot. Okay, so this z, let's call z as x plus iy. Look at this. This z is equal to x plus iy. Okay, so z dot will be x dot plus iy dot. Z double dot will be x double dot plus iy double dot. Okay, so that's what I am going to do here. If you add these two terms, first term will be x double dot plus iy double dot, which I call z double dot. Okay, plus second term will be gamma times x dot plus iy dot, which is x dot plus iy dot will be z dot. Third term will be omega 0 square times x plus iy, which is z. Okay, so this equation looks, equation 3 looks exactly similar to equation 1 or equation 2, but the only difference is that now in equation 1 and equation 2 x and y are real variables, but in equation 3 z is a complex variable. Okay, so we want to solve this in terms of complex variables. Now in this differential equation, this is a differential equation with constant coefficients. Okay, see the coefficient of z double dot for d square z by dt square is 1. Coefficient of dz by dt or z dot is gamma, which is also a constant. Coefficient of z is omega 0 square, it's also a constant. So when you have a differential equation with constant coefficients, we can use a trial solution, and a good choice of a trial solution in this case is that z is equal to z0 e raised to alpha t, where z0 and alpha are two parameters which are two variables which are independent of t, which are independent of time. Okay, so we use this as a trial solution. Okay, so let us substitute this in equation 3. In order to substitute this in equation 3, we should know what is z dot. So what is z dot? When you differentiate this once, z0 and alpha are constants, that is they are independent of t. So z0 e raised to alpha t, when you differentiate, what you get? Alpha times e raised to alpha t. Okay, now what is z double dot? Again z0 is constant, alpha is constant. You have to differentiate e raised to alpha t once again. That is, when you differentiate it once more, you get again alpha e raised to alpha t. So we get alpha square here e raised to alpha t. Right? So let us substitute these three, that is equation 3, equation 4 and equation 5 in equation, sorry, my numbering is different now. This is equation 4, equation 5 and equation 6. So let us substitute equation 4, 5 and 6 in equation 3. Let us see what we get. So this z double dot becomes z0 alpha square e raised to alpha t plus gamma times z dot is z0 alpha e raised to alpha t plus omega 0 square times z0 e raised to alpha t equal to 0. E raised to alpha t we can factor out from all the terms. In fact, we can remove z0 e raised to alpha t, we can remove from all the terms. Then what do you get? Alpha square plus gamma times alpha plus omega 0 square equal to 0. You get this. The differential equation is converted into an algebraic equation, right? Look at equation 3. This is a differential equation. When you do this substitution, this is converted into an algebraic equation. Okay. Now this is a quadratic equation in alpha, so you can get the you can get the solution. you know the solution of a quadratic equation. So what are the solutions? So let us say alpha is equal to, it's like if it is ax square plus bx plus c equal to 0, then what is solution? X is equal to, maybe I will write it here. Okay, so this equation 7 is a quadratic equation of the form ax square plus bx plus c equal to 0. What is the solution? X is equal to minus b plus or minus root of b square minus 4ac by 2a. This is the solution. So if you do this for equation 7, okay, a is 1, b is gamma, and c is omega 0 square, right? Instead of x, you have alpha. So alpha is equal to minus gamma plus or minus square root of gamma square minus 4 omega 0 square divided by 2. A is 1, right? So this is it. Now what you can do is, I will take this 4 outside from the square root. So you can write this as alpha is equal to minus gamma plus or minus. When you take 4 outside, it becomes 2. Square root of, here it is gamma square by 4 minus omega 0 square whole divided by 2. So you can divide both terms with 2. So you have minus gamma by 2 plus or minus square root of gamma square by 4 minus omega 0 square. This is not r but gamma. Okay, gamma square by 4 minus omega 0 square. So you have two values for alpha. Maybe alpha 1 is so that corresponding to that plus symbol. So let me write, let alpha 1 is equal to minus gamma by 2 plus square root of gamma square by 4 minus omega 0 square, and alpha 2 equals minus gamma by 2 minus square root of gamma square by 4 minus omega 0 square. So you have two values for alpha. Now you can substitute these two values in the trial solution. Look at equation 4. This is a trial solution. Now we can have two values for alpha, alpha 1 and alpha 2. Okay, so you can have a trial solution. I mean, the real solution can be some constant z0 times e raised to alpha 1t, and another solution can be another constant into e raised to alpha 2t. Okay, one solution can be some constant times e raised to alpha 1t. That can be one solution, or another solution can be some constant into e raised to alpha 2t. So e raised to alpha, some constant times e raised to alpha 1t and a constant times e raised to alpha 2t are two possible solutions. These constants can be different. See, this is a homogeneous equation. Equation 3 is a homogeneous equation. Therefore, if you multiply a solution with a constant, you will get that constant times the solution will also be a solution. Okay, and so what is a general solution? So general solution will be, this is also a linear differential equation. So this is a homogeneous differential equation as well as a linear differential equation. So if you have two solutions, like some constant times e raised to alpha 1t and another constant times e raised to alpha 2t, then a linear combination of these two, or let us say if e raised to alpha 1t and e raised to alpha 2t are two solutions, a linear combination of these two solutions will also be a solution of this equation. Why? Because it's a linear equation. Okay, so we have I have mentioned that equation 3 is a homogeneous equation as well as a linear equation. So you do this as a homework. That is, what is a linear differential equation? Once you see a differential equation, can you identify, how do you identify whether it's a linear differential equation or a non-linear differential equation? Or once you see a differential equation, how do you identify it as a homogeneous equation or a non-homogeneous equation? Equation 3 is both linear and homogeneous. Okay, now that question is there. You can address it separately. So the complete solution now is, so one solution can be e raised to alpha 1t, another solution can be e raised to alpha 2t. So a general solution is a linear combination of e raised to alpha 1t and e raised to alpha 2t. So we can write the general solution of, so we are not writing the solution of equation, equation 3. So the general solution of equation 3 is, so the solution of equation 3 I can write as z is equal to some z1 e raised to alpha 1t plus some z2 e raised to alpha 2t, where the values of alpha 1 and alpha 2 are given here. So what about our numbering? We have reached equation 7. Maybe the values of alpha 1 and alpha 2 we can write as equation 8, and this general solution is equation 9. Okay, alpha 1 is minus gamma by 2 plus root of gamma square by 4 minus omega 0 square, and alpha 2 is minus gamma by 2 minus root of gamma square minus omega 0 square. So one value in the solution, one solution can be e raised to alpha 1t, another solution can be e raised to alpha 2t. A general solution is a linear combination of the two, where z1 and z2 are two constants. In general they can be complex constants. Okay, they can be complex constants. So this is the general situation. Now we will consider three special cases depending upon the, see, in the expression of this alpha 1 and alpha 2 you have this square root, right? You have this term square root of gamma square by 4 minus omega 0 square. So depending upon the relative values of gamma square by 4 and omega 0 square, gamma is the damping term, omega 0 is the natural frequency of the oscillator. So depending upon their relative strength, okay, there can be three different cases. So let us consider each case separately. Case 1, this is called underdamped oscillator. Okay, what I mean by underdamped is this term gamma square by 4, this damping term is less than omega 0 square. Okay, so the damping term is less than the natural frequency term. Okay, we can write this condition in different way. If you take square root on both sides, gamma by 2 is less than omega 0, or we can take 2 to the right side, that is gamma is less than 2 omega 0. That also is possible. But let us say we have written the square root in this form, gamma square by 4 minus square root of gamma square by 4 minus omega 0 square. So simply take this idea, this damping term is less than natural frequency term. That's called underdamped. Okay, very low damping compared to the natural frequency. Then what happens? Then you can see that this alpha 1, this square root term, this term is less than this one. So you have inside the square root you have a negative quantity, right? Square root of a negative value. So something like square root of minus beta, right? Then that you can write as what you can do is square root of minus 1 you can take out as some I, and you can write this as square root of beta. That means what I am going to do is, see, gamma square by 4 is less than omega 0 square. So I will write this square root as a positive number. So for that I will take a minus sign outside. Okay, so we can write that square root part. Look at this. That square root part we can write square root of gamma square by 4 minus omega 0 square. We can write as square root of minus of omega 0 square minus gamma square by 4. Okay, this gamma square by 4 is less than omega 0 square. So this omega 0 square minus gamma square by 4 will be positive quantity, and this term is square root of minus 1. So this I can write as I times square root of omega 0 square minus gamma square by 4. Now let me define a frequency omega 1 as square root of omega 0 square minus gamma square by 4. Okay, therefore what happens is that exponential part, this alpha 1 will look like alpha 1 and alpha 2 can be written in terms of omega 1. There will be an extra I term. Okay, so what you have is alpha 1. So this means alpha 1 is equal to minus gamma by 2. See here, you have minus gamma by 2 plus the square root. Okay, plus the square root. And what is that square root now? Square root now has becomes I times this, I times omega 1. So we have plus I times omega 1, and alpha 2 is minus gamma by 2 minus I times omega 1, where omega 1 is square root of omega 0 square minus gamma square by 4. Okay. So what is our solution? Now we can write equation 9 becomes, so equation 9 becomes, let me call this as equation 10. Okay, now equation 9 becomes z is equal to z1 e raised to, instead of alpha 1 I will substitute this minus gamma by 2 plus I omega 1 t plus z2, see here equation 9, z1 e raised to alpha 1 t plus z2 e raised to alpha 2 t, right? So instead of alpha 1 I have substituted. Similarly for alpha 2 e raised to minus gamma by 2 minus I omega 1 t. Okay, let us simplify this. E raised to minus gamma by 2 into t is common in both cases, so I will take it out. My e raised to minus gamma by 2 into t. Okay, what is the remaining term? Z1 e raised to I omega 1 t plus Z2 e raised to minus I omega 1 t. Okay, let's give next equation number. This is equation 11. So this is our solution. E raised to minus gamma by 2t, z1 e raised to I omega 1t plus z2 e raised to minus I omega 1t. This is the solution of equation 3, this one, which we have, which is the differential equation. We have written differential equation of damped harmonic oscillator, which we have rewritten in terms of complex variable z. But our real harmonic oscillator, damped harmonic oscillator, is having real variable x or y. Okay, so how do we get back the solution in terms of x or y? Either x or y. So we have obtained a solution in terms of z. Okay, how do we get back the solution in terms of x or y? So what you can do is, on both sides, you let us rewrite this in Cartesian form in x and y. So left hand side you can write x plus iy is equal to e raised to minus gamma by 2 into t. This z1 and z2 are constants. Okay, and z1 is x1 plus iy1. So naturally x1 and y1 are constants, whereas on the left side x and y are variables at the time t. Okay, x1 plus iy1 e raised to I omega 1 t plus x2 plus iy2 e raised to minus I omega 1 t. Okay, and okay, e raised to I omega 1 t also we have to expand, express. Okay, what is e raised to I theta? See, e raised to I theta we can write as cos theta plus I sin theta, de Moivre's theorem. Okay, using that, if you rewrite this, you get x1 plus iy1 into, this is cos omega 1 t plus I sin omega 1 t plus x2 plus iy2 cos omega 1 t minus I sin omega 1 t. Okay, why we are writing it like this? See, what we are going to do is, we are expanding the right side, and then on the left side and right side, if you equate the real variables, that means on the left side the real variable, real part, okay, real part is x, and on the right side if you equate the real part, you get an expression for x. Similarly, if we equate the imaginary part, you get an expression for y. So the real solution of the damped harmonic oscillator, you can write either in terms of x or in terms of y. If you equate the real parts on both sides, you will get the answer in terms of x. If you equate the imaginary parts on both sides, you will get the answer in terms of y. That's what we are going to do. For that, we have to expand this. So this is equal to e raised to minus gamma by 2 into t. Okay, so let us look at this. First you multiply all the terms with x1 and then y1. You have 4 terms. Okay, let me try to simplify this. So x1 times cos omega 1t is there, and then you have here you have x2 times cos omega 1t is there. Or from both, if you take cos omega 1t outside, you will get x1 plus x2 into cos omega 1t. You have a term like this. Okay, and then the next term you multiply x1 with I sin omega 1t, right? X2 with minus I sin omega 1t. So if I take I sin omega 1t outside, you have x1 minus x2. So you have plus I times x1 minus x2 sin omega t, sin omega 1t. Okay. So I think we have completed all the terms involving x1 and x2. That means all the x terms are completed. Let us look at the y terms. So if I multiply this cos omega 1t with iy1, you have an imaginary term here, imaginary part here, iy1 times cos omega 1t. Here also you have iy2 times cos omega 1t. So if I take I cos omega 1t outside, you have I times y1 plus y2 cos omega 1t. Okay. Then you have another term iy1 times I sin omega 1t. I into I is I square is minus 1. So you have minus y1 sin omega 1t. Here you have iy2 times minus I sin omega t. So I square is minus and minus will be plus. So you have y2 sin omega 1t. So what you have is y2, if I take sin omega 1t outside, you have y2 minus y1. So you have y2 minus y1 sin omega 1t. Okay, you can check whether this is correct. Yeah. Now you have two real parts. You have two terms involving real quantities only. So in other words, on the right hand side, if you rearrange x1 plus x2 cos omega 1t and this y2 minus y1 sin omega 1t, this is the real part on the right side. Then you have two terms involving I, imaginary part. So I times, that means x1 minus x2 sin omega 1t, and here also y1 plus y2 cos omega 1t. These are imaginary parts. Okay, so if you equate real parts on both sides of this equation, on the left hand side you have x, on the right side if you take equate the real parts, you get an expression in terms of x. Okay, remember x1, x2, y1, y2 are constants. On the left hand side you have x of t and y of t. X is a function of t and y is a function of t. So if I equate the real parts on both sides, we get x of t is equal to e raised to minus gamma by 2 into t x1 plus x2. Okay, here equating the real parts. On both sides. x1 plus x2 cos omega 1t plus y2 minus y1 sin omega 1t. This is what we will get. Okay, similarly if you equate imaginary parts on both sides, you have y of t is equal to, what do you get? Y of t is equal to y1 plus y2 cos omega 1t plus x1 minus x2 sin omega 1t. Is it x1 minus x2 or x2 minus x1? X1 minus x2. Okay, yeah. Okay, so these are identical equations. We are just interchanging x1, x and y. That's all. So I hope this is correct, or is there any correction? Minus y1 plus y2, this is correct only. So this is our final solution. So we can this x1 and x2 are constant, so let this is equal to some constant b, and this is equal to some constant c. So our solution you can recast as e raised to minus gamma by 2t into b cos omega 1t plus c sine omega 1t, something like this. Okay, this is one way of writing, or we can also write x of t as remember the previous class on ideal harmonic oscillator. The solution of an ideal harmonic oscillator you can either write in terms of b cos omega 0 t plus c sine omega 0 t, or you can write this in terms of another way, some constant a, and of course this exponential part is there, e raised to minus gamma by 2t into cos omega 1t plus phi, where phi is some initial phase or phase constant. So in this form, see what is the equation number. I think we have reached equation 11. So this is equation, we can call it equation 12. This is equation 13. So 12 and 13 are identical forms. Here we have two constants, two unknown constants b and c, which we have to evaluate from initial conditions. Here also we have two unknown constants a and phi, which we have to evaluate from initial conditions. Okay, these are two ways of writing the same solution. And in order to understand how we can reach from one to the other, or what is the relationship between a and phi with b and c, you can express a and phi in terms of b and c. What is the relation? And for this you see the discussion on ideal harmonic oscillator in the previous class. Okay, so we can use either form, they are identical, they are interchangeable, these constants are connected, so we prefer this form. Okay, so x of t is equal to a e raised to minus gamma by 2t cos omega 1t plus phi. Now let us compare this with the case of an undamped harmonic oscillator. Okay, for an undamped harmonic oscillator, the expression for position, the solution was a cos omega 0 t plus phi. Okay, this is, let's call it equation 14. Let's compare equation 13 and 14. So what you get is one is that the amplitude for an undamped oscillator, amplitude is constant. For a damped oscillator, amplitude exponentially decreases. Amplitude is a e raised to minus gamma by 2 into t. This is the amplitude for a damped oscillator. For an undamped oscillator, amplitude is constant. Okay, so this is for undamped, this is for damped. Amplitude is exponentially decreasing. Okay, and second, we notice that in undamped oscillator the angular frequency is omega 0, which is square root of k by m, and this has changed to omega 1 now. The frequency is different. What is the expression for omega 1? Omega 1 is omega 0 square minus gamma square by 4. That damping factor is there. Suppose gamma is 0. If gamma is 0, omega 1 is same as omega 0, just like undamped oscillator. Similarly, here also if gamma is 0, then this exponential part will be 1 and the amplitude will be constant, just like an undamped oscillator. So the effect of damping in the case of underdamped case, if the damping constant is gamma square by 4 is less than omega 0 square, if the damping is low, then the effect is that the solution of the damped oscillator is an oscillatory solution. See, you can have this cosine part here. This is the oscillatory part. It's an oscillatory solution, but the amplitude of oscillations is no longer constant. It exponentially decreases. That is the main thing. Okay, so in the underdamped case, solution is an oscillatory solution with an exponentially decreasing amplitude. And second thing is that the frequency of oscillation is also less than the natural frequency of oscillation. It is less than omega 0. Okay. Okay, let us now try to plot equation 13. That means let us see how the the instantaneous position varies with time for a damped harmonic oscillator. For comparison, let me first go back to our diagram, similar plot for an undamped oscillator. So let us first consider the plot of an undamped oscillator. Okay. So for an undamped oscillator, if you plot position as a function of time, the important point is that the amplitude will be a constant. Amplitude is A, right? I just assume that the initial phase is 0. That means phi is 0. Therefore, if you are plotting a cosine function at time 0, you get a maximum amplitude. Okay, something like this. Okay, amplitude is a constant. A, its magnitude is A. But what about a damped oscillator in this case, with the underdamped oscillator? Okay. Now, in the case of an underdamped oscillator, there can be further two situations. Okay. For an oscillator, that's what we have discussed now. So, for an underdamped oscillator, see, the important point is that the amplitude is exponentially decreasing. There is an oscillatory part, but the amplitude will be exponentially decreasing. Now, there can be two situations. Light in underdamped case, okay, lightly damped case and heavily damped case. Okay, the point is how this gamma square by 4 and omega 0 are related. Okay, so already we have seen that for an underdamped case, gamma square by 4 is less than omega 0 square. Okay, now let me consider two further cases. One is lightly damped. Okay, lightly damped, I mean this gamma square by 4, gamma square by 4 is less than omega 0 square, but in the case of lightly damped case, it's very small compared to omega 0 square. Okay, so what you get is this omega 1 will be approximately equal to omega 0. Okay, we know the expression for omega 1. Omega 1 is C, omega 0 square, square root of omega 0 square minus gamma square by 4. So in underdamped case, generally gamma square by 4 is less than omega 0 square. But if gamma square by 4 is very small compared to omega 0 square, omega 1 will be very close to omega 0 square. Okay, so this omega 1 will be very close to omega 0. So in that case, the damping is very low. Okay, so if you draw a lightly damped oscillator here, okay, see, in general what happens is the amplitude will be exponentially decreasing, but the decrease will be very, very low. The amplitude will be exponentially decreasing, but the decrease will be very slow, something like this. So the situation is something like this. So you can see that over a period of time, the amplitude will be exponentially decreasing, but the decrease is low, it's slow. Okay, this is the case with the lightly damped oscillator. Now another possibility is heavily damped oscillator. In heavily damped oscillator, gamma square by 4 is again less than omega 0, but it's close to omega 0. Its value is of the order, not close to, but of the order of omega 0. That means it is significant. It's not very small compared to omega 0. So in that case, what happens is this omega 1 will be very small compared to omega 0. Omega 1 will not be in the neighborhood of omega 0. It will be very small compared to omega 0. So it's a heavily damped oscillator. So if you plot a heavily damped oscillator, okay, this is undamped and this is lightly damped. Okay, now if I plot a heavily damped oscillator, it's still oscillatory, it's still underdamped case, but the damping is very strong. Okay, so the effect is that this x of t, the effect is that the amplitude will be very fast decreasing exponentially, very fast. Okay, so it is something like this. Okay, see, its damping is very strong. Okay, so this you can look at the three plots. In underdamped oscillator, the amplitude remains constant. Okay, amplitude is remaining constant here. There is no change in the amplitude, but in a like in a lightly damped oscillator, the amplitude is exponentially decreasing, but the decrease is slow. In a heavily damped oscillator, amplitude will be decreasing very fast, very rapidly. Okay, so this underdamped oscillator you can classify depending upon the relative value. If gamma, the damping is very small compared to damping constant is very small compared to the natural frequency, then it is lightly damped. If it is significant compared to the natural frequency, that means that if it is of the order of natural frequency, then it is heavily damped. Now in the lightly damped case, this new frequency omega 1 will be very close to omega 0. It's almost like an underdamped oscillator, like a undamped oscillator. Okay, but in heavily damped case, omega 1 will be very small compared to omega 0. Okay, so that depends upon the relative values between damping constant and the natural frequency. So this is the situation for an underdamped oscillator where gamma square by 4 is less than omega 0. Okay, let's go to the opposite case. Gamma square by 4 is greater than omega 0. This is called overdamped case. Now the condition is that gamma square by 4 is greater than omega 0 square. Okay, now then what is the solution? We know that alpha is equal to minus gamma by 2. The two solutions are plus or minus, or two values of alpha are minus gamma by 2 plus or minus square root of gamma square by 4 minus omega 0 square. These were the two solutions, or these two values of alpha correspond to the two solutions. Now here, when gamma square by 4 is greater than omega 0 square, let's take gamma square by 4 outside the square root. Then when it comes outside, you have gamma by 2. Okay, now inside the square root, this term will be 1 minus omega 0 square divided by gamma square by 4. Okay, look at this expression. Let's try to understand this expression. Here inside the square root, this term denominator gamma square by 4 is greater than omega 0 square. That is the overdamped condition. Okay, gamma square by 4 is greater than omega 0 square. So here denominator is greater than numerator. So this term will be less than 1. Less than 1. Okay. And what about the square root? Inside the square root you have 1 minus a quantity less than 1. That means the square root will be positive. Okay, it will be positive, but its total value will be less than 1 because you are subtracting something from 1. Okay, so its value is less than 1. Okay, so what you have is alpha is equal to minus gamma by 2 plus or minus gamma by 2 into a quantity less than 1, a positive quantity, less than 1. Let us say something like 1 by 2 or 1 by 4. So you are multiplying gamma by 2 with a positive quantity less than 1. So this term will be gamma by 2 into something like 0.1, something like that. Okay, less than 1, a positive quantity less than 1. So this will be less than gamma by 2, this term. Okay, see, this first term is minus gamma by 2. Now you have two possibilities here, plus or minus. Okay, when you add to minus gamma by 2 a quantity, one possibility is add something to this, but when you add it, that quantity is less than gamma by 2. Okay, that means the whole thing, this is something like minus gamma by, let's say minus 10. What you add here is its magnitude is less than gamma by 2. Let's say it is 2. So when you have minus 10 plus 2, the whole quantity is negative. Okay, you are adding to minus gamma by 2 a positive quantity whose value is less than gamma by 2. Why? Because you are multiplying gamma by 2 with a positive quantity less than 1. So this quantity ought to be less than gamma by 2. So this first possibility, when you choose the upper sign plus, the resultant alpha value is negative. When you choose the lower sign minus, definitely it is negative because minus gamma by 2 minus something like minus 10 minus 2 minus 12. Okay, in the first case it is minus 10 plus 2, that is minus 8. So in either case the both values of alpha are, in either case the value of alpha is negative, which implies both alpha 1 and alpha 2 are negative. Yes, negative values. Then we can write z of t, the solution, general solution, as z1 e raised to see, alpha 1 and alpha 2 are negative, so I can write this as minus of modulus alpha 1 t. Next solution is e raised to minus of modulus alpha 2 t. Let us say the value of alpha 1 and alpha 2 are, as in our previous example, minus 12 and minus 8, right? So we can write it like this: e raised to minus of modulus of alpha 1 t, e raised to minus of modulus alpha 2 t. This is the complex solution. You can equate the real part again on both sides. So left hand side I can write as x of t plus I times y of t is equal to, z1 and z2 are constants, remember. So x1 plus I y1 e raised to minus alpha 1 t plus x2 plus I y2 e raised to minus modulus alpha 2t. Now equating the real parts on both sides, you get an expression in x. Equating the imaginary parts on both sides, you get an expression in y. So x of t is equal to x1 e raised to minus modulus alpha 1 t plus x2 e raised to minus modulus alpha 2t. Or instead of x1 and x2 we can use a and b. So we have position, instantaneous position is a e raised to minus alpha 1 t plus b e raised to minus alpha 2t. This is the next equation 50. We can see that there is no oscillatory term here. Okay, both terms are exponentially decreasing terms. There is no oscillation, there is no sine or cosine term. That means the amplitude will be decreasing exponentially fast without any oscillation. This is over damped case. So when there is too much damping, gamma square by 4 is greater than the natural frequency. The damping term is greater than the natural frequency term. Then there is no more oscillation. The amplitude will be exponentially decreasing very fast. Okay. There is only exponential decrease here, no oscillation. Now consider a third case, case 3. This is called critically damped oscillator. Critically damped oscillator. The condition is that gamma square by 4, the damping term, is exactly equal to omega 0 square. Okay, then what is the value of alpha? Minus gamma by 2 only, because the general expression for alpha is minus gamma by 2 plus or minus root of gamma square by 4 minus omega 0 square. If gamma square by 4, this damping factor, is exactly equal to the natural frequency term, then alpha is simply minus gamma by 2. Okay, so alpha has only one term. Then the solution is z of t is equal to some value z0 e raised to alpha t minus gamma by 2 into t. Alpha has only one term. Okay. Now the problem with this solution is that this solution contains only one unknown constant z0. Gamma is not an unknown constant because gamma is simply b by m. Okay. So we know the value of b and m. So gamma is not an unknown. The unknown constant here is z0, which has to be evaluated from the initial conditions. But our original differential equation is a second order differential equation for the damped harmonic oscillator. It's a second order differential equation. When you write the general solution of a second order differential equation, there should be two unknown constants which have to be evaluated from initial conditions. We have to supply two initial conditions. So this solution is incomplete. Okay. So what is our or why we get such a solution? The reason is that we started with a trial solution, something like z0 e raised to alpha t. We substituted it in the original differential equation of z, and we got two values of alpha, right? So in that trial solution, we have put a constraint, a condition that both z0 and alpha are independent of t. Okay, now let us remove that constraint. Let us assume that the original trial solution, the z0 can be a function of t. Z0 can vary with t. Okay, Z0 can parametrically change with t. So let us go back to our original differential equation. What was our original differential equation? Z double dot plus gamma times Z dot plus omega 0 square times Z equal to 0. Okay, now we can go back to the trial solution and assume that the amplitude changes with time. Okay, so let us say the trial solution, we start with another trial solution. Let Z of t is equal to, instead of Z0, let me take some u which is a function of t, e raised to minus gamma by 2 into t. Okay, I am not using e raised to alpha t because alpha is minus gamma by 2, we know that. Okay, in this condition alpha has a single value only. But this amplitude, we have taken it as parametrically changing with respect to time. It's no longer a constant. Now I want to substitute this trial solution in the differential equation. For that we need to have the values of z dot, z double dot. So what is z dot? Let's call this as equation 16. Previously we have used equation 15, right? Equation 16. So z dot is derivative of the first function u dot, second function is like that, plus first function into derivative of second function. So minus gamma by 2 e raised to minus gamma by 2 into t. So let me take gamma by e raised to minus gamma by 2 into t outside. So u dot minus gamma by 2 into u e raised to minus gamma by 2 into t. This is z dot. Now we need also z double dot. So z double dot is derivative of first function. So let's take the entire term in the bracket as the first function. So u double dot minus gamma by 2 is a constant into u dot. Derivative of first function into second function plus first function into u dot minus gamma by 2 into u. This is first function into derivative of second function minus gamma by 2 e raised to minus gamma by 2 into t. Okay. This can be further simplified by taking e raised to minus gamma by 2 into t outside. So what you get? U double dot, and when you take e raised to minus gamma by 2 into t outside, here you have minus gamma by 2 u dot. Here we have a minus gamma by 2 outside. Okay. When you multiply this minus gamma by 2 with both the terms here, because we are taking only e raised to minus gamma by 2 into t outside. So first term becomes minus gamma by 2 into u dot. You can add it with this one. Okay. So what you get is minus gamma into u dot. Okay, so that there are two u dot terms that you can combine. What about this term? You have minus gamma by 2 here, another minus gamma by 2 here. So you have minus of minus will be plus. Okay, we have gamma square by 4 u times e raised to minus gamma by 2 into t. This is Z double dot. Okay, so let us substitute. Okay, the expression for Z dot we can call equation 17. Final expression for Z double dot we can call equation 18. Okay, so let us substitute equation 16, 17 and 18 in the differential equation of Z. Z double dot, this original number is I think 3. Z double dot minus plus gamma times Z dot plus omega 0 square times Z equal to 0. So let us substitute that. So we have Z double dot, that is u double dot minus gamma times u dot plus gamma square by 4 times u into e raised to minus gamma by 2 into t. Then next term is gamma times Z dot. Z dot is this u dot minus gamma by 2 into u e raised to minus gamma by 2 into t. This is gamma times Z dot, and then you have omega 0 square times Z. Okay, so that is plus omega 0 square times u e raised to minus gamma by 2 into t equal to 0. Okay, now we can factor out e raised to minus gamma by 2 into t. Okay, that we can take out. So what are the different other terms? U double dot minus gamma u dot plus gamma square by 4 times u plus in the second term, this gamma you have to multiply with the two terms in the bracket. So gamma times u dot, so plus gamma times u dot minus gamma square by 2 times u plus omega 0 square. In the third term we have omega 0 square times u equal to 0. Okay, minus gamma times u dot and plus gamma times u dot will cancel, plus gamma square by 4 times u minus gamma square by times u. So we have u double dot plus gamma square by 4 minus gamma square by 2 will be minus gamma square by 4 times u plus omega 0 square times u equal to 0. Okay, now this is equal to u double dot. Okay, u is common for these two terms, so we have omega 0 square minus gamma square by 4 u equal to 0. Okay, but we are in the third case, critically damped case, where the condition is gamma square by 4 is equal to omega 0 square, right? Then if gamma 0 square is equal to omega 0 square by 4, okay, sorry, if gamma 0 square is equal to omega square by 4, then this is equal to 0. Okay, so what you have is u double dot equal to 0. If you integrate once, u dot can be some constant b. It can be a complex constant, but it's independent of time. Integrate one more time, then u is equal to bt plus another constant a. A also can be a complex constant. So we have this result u is equal to a plus bt, where in general a and b can be complex constants. So what is the value of z? What is our solution now? A plus bt times e raised to minus gamma by 2 unit. In general, a and b can be complex constants. Now equating real and real or imaginary parts on both sides. Okay, we can write, if you equate real parts on both sides, x of t is equal to this a and b you can express as real part plus imaginary part. Okay, so let me write this, let us say a is equal to some capital A times I a prime. B is equal to some capital B times I b prime. Okay, and z is x plus iy. So if I equate real parts on both sides, we get a plus bt times e raised to minus gamma by 2 into t. Again, the solution is not oscillatory. There is exponentially decreasing part here. Okay, e raised to minus gamma by 2 term is 2t term is there, but see, it's not only exponential decrease. There is a linear increase with respect to t also. Okay, so there is a part which is linearly increasing with t, and also there is an exponential decrease. Okay, that is the case with the critically damped situation. Okay, so there are generally three cases. Underdamped case, where the damping factor gamma square by 4 is less than omega 0 square. Overdamped case, where gamma square by 4 is greater than omega 0 square. And critically damped case, where gamma square by 4 is equal to omega 0 square. And here the more interesting case is underdamped case, where the damping factor is less than omega 0 square. This one, gamma square by 4 is less than omega 0 square, and there the solution, we have seen that it is oscillatory solution. Okay, the difference is that there are two differences. One is that the amplitude changes to exponentially decreasing part, a e raised to minus gamma by 2 into t. Okay, second is that the natural frequency of oscillation omega 0, which is square root of k by m, it changes to omega 1, which is square root of omega 0 square minus gamma square by 4. And in underdamped case, there can be two situations. Lightly damped case, where the damping factor is very small compared to omega 0 square. In that case, omega 1 is of the order of omega 0. And here, in the case of an undamped oscillator, this is the oscillation, amplitude is constant. But in a lightly damped case, amplitude is no longer constant, it's changing. You can see that the overall amplitude is exponentially decreasing. But the point is, the decrease is very slow. There is a decrease in amplitude. In heavily damped case, the damping factor is of the order of omega 0. Therefore, gamma square by 4 is of the order of this. I have to write omega 0 square here. Here, this is omega 0 square. Then in that case, omega 1 will be very small compared to omega 0. That's a heavily damped case. Usually this lightly damped case and heavily damped case we can express in terms of the ratio between gamma and omega 1. Okay, for example, in this case, gamma by 2 omega 1. Okay, this value will be very small compared to 1, let us say 0.05. Whereas in a heavily damped case like this ratio will be significant. It is still less than 1, but it is somewhat significant, of the order of 1. Let us say gamma by 2 omega 1 is 0.25 here, 1 by 4. Okay, it's a significantly large value. So if gamma by 2 omega 1 is very small compared to 1, like in this case 0.05, then it's a lightly damped case. Okay. This happens when gamma square by 4 is very small compared to omega 0 square. Okay, then this ratio also will be very small compared to 1. And in a heavily damped case, gamma square by 4 will be somewhat of the order of omega. It's still less than omega 0 square, but somewhat of the order of omega 0 square. Then what happens is this ratio gamma by 2 omega 1 will be significantly large, 0.25, less than 1 but significantly larger. So in that case the amplitude far rapidly decreases exponentially. This is a more interesting case, this underdamped situation, okay, where there is oscillation. This is a solution. X of t is equal to a e raised to minus gamma by 2t cos omega 1 t plus pi. So it's an oscillatory solution, except the amplitude part is exponentially decreasing. It's no longer a constant. And also the frequency is no longer natural frequency. It contains both natural frequency as well as the damping term. Root of omega 0 square minus gamma square by 4. Okay, so this is our discussion on damped harmonic oscillator. So when in a real situation, the oscillations are damped oscillations. For example, a simple pendulum is oscillating in the lab in the air, and the air exerts a viscous force proportional to velocity, instantaneous velocity, and opposite to the direction of velocity. So any real oscillator is a damped oscillator. And also, as I have mentioned in the beginning, even though we have discussed a mechanical oscillator, the theory that we have studied is valid for even electric circuits where current is oscillating, for example in an LC circuit, and there this viscous force, the counterpart of the viscous force is the resistance in the circuit. Okay, that's all.